All right, so in this video, we're going to talk about, or continue talking about, our trig powers. Looking at our first example here, we have tangent secant to the fourth d theta. And so to get this started, I'm just going to rewrite it as tangent theta secant theta with a secant cube theta off to the end there. Now, again, it's all up to us to decide what's the easiest way to get where we're going. And the best way to do this is to really understand things you know. And the things you know would be, if you let u equal secant of theta, then our du would be secant theta tangent theta d theta. In other words, a perfect fit. And so for this one, it really wasn't that we had to use identities as much as it was just split this thing up into something where you could select your u accordingly and your du would take care of the rest. So when all said and done in this problem, all we would have to integrate is a u cubed du, which would give us this 1/4 secant to the fourth theta plus c as our final answer. So don't overthink some of these. I know, again, guys, it's going to be a painful working through and getting through the growing pains of these types of problems. But trust me, the more you work, the better you will be at recognizing the patterns, and the better you'll be at recognizing what is going to work and what isn't going to work. All right, so this next example, I'm actually going to work with you guys two different ways. And so the first way is going to be more using some trig identities that I feel like lead you to a result a little more quickly. And the second way, I'm going to use a different set of trig identities that's going to then take you back into a little bit of Calc 1. Okay, so for this first thing that I'm going to do, I'm going to go ahead and rewrite secants and tangents in terms of sines and cosines. So if I do this, for the tangent squared in the denominator, which is cotangent squared, that's going to be a cosine squared over a sine squared. And then this secant to the fourth in the numerator is going to be our 1 over cosine to the fourth in our denominator. Okay, so now what I'll consider next is the fact that this cosine squared and two of those can go away, leaving me with what appears to be a little bit of a simpler approach. So that's going to be a sine squared there and a cosine squared there. And I'm going to go ahead now and rewrite this a little differently. So if I can go ahead and follow me on this, I'm going to erase those cosine squareds right there, and I'm going to put that like that. All right. The reason why I went ahead and wrote it like that is because of what I'm about to do next. If I put a 2 right here, then this is one of my double angle identities. Now, I can't just put a 2 there and be done. I also need to put a 2 on the top. But remember, this is a 2 squared. So I need to put a 4 on the top. Okay? So having done this now, this would be a 4 with a 1 over sine of 2x, right? This guy right here, this is sine of 2x, but then it's squared. So I'll put my squared in there, which actually, as I pointed out at the beginning, is pretty convenient because now it's going to give me this integral of cosecant squared, which is one of them I actually know. That's one from Calc 1. We would need a u sub here, but that's pretty basic at this point, and we get a -2 cotangent of 2x plus c as our final answer. Okay, so I feel like this is more of a direct approach. That being said, you're at the mercy of recognizing this identity and being able to execute it properly. Now, the other way that I want to look at this problem is not so much going into sines and cosines, but leaving things in terms of secants and tangents. So in the numerator, I'm going to call this a secant squared x, and then a tangent squared x in the denominator. And then for one of these guys, I'm going to use our Pythagorean identity. So that's going to be a 1 plus tangent squared x times secant squared x all over tangent squared x dx. Now, having done this, this is going to give me an opportunity for a u sub. If I let u equal tangent of x, then the du is going to be our secant squared of x dx. So you might now be able to start seeing why leaving things in terms of tangent was okay, as long as I had this additional secant squared off to the side. So now the integral will be a 1 plus u squared over u squared du. And now we can treat it as a calc 1 integral. I'll go ahead and split that up into 1 over u squared plus 1. We'll add 1 and divide all the way through. So that's going to be a negative 1 over u plus c. And finally, we'll get a negative 1 over tangent of x plus tangent of x plus c, which is negative cotan of x plus tangent of x plus c. So both options are fine. I don't really care which one you use, but both will get you to where you need to go for this problem. Also, it's worth mentioning, these answers look pretty different, don't they? And so if you're coming up with something that looks a little bit different than maybe the book or something else, you might not be wrong. It could have just been some other identity that was used to get to your final answer. So please don't automatically assume you're incorrect. You will need to further investigate it to make sure it is in fact what it is supposed to be, but you might get some different looking answers on these types of problems as well. All right, so for this example, we're going to handle this one similar to the last one, where I go ahead and I just take advantage of the fact that cosecants and cotangents in general work well together. So we'll call this cosecant squared and cosecant squared. And then I'm going to keep this cotangent to the 6th all alone over here. And so remember, if you are going to use a u sub, pick something that you are able to then take the derivative of, and it's still going to be a perfect fit for the integral. And in this case, I'm looking like I want to let my u equal cotangent, so that my du is going to be that negative cosecant squared. So let me go ahead and take this one as well and use the Pythagorean identity, converting it into some cotangents. So cosecant squared, and then this would be 1 plus cotangent squared with a cotangent to the 6th off to the side. And as I mentioned before, now if we let u equal cotangent of x, then du is going to be negative cosecant squared of x dx. So a nice fit. We'll have a negative 1 plus u squared times u to the 6th du. I'll go ahead and distribute the u to the 6th. And we can go ahead now, add 1 and divide all the way through. So negative 1/7 cotangent to the 7th of x minus 1/9 cotangent to the 9th of x, finally plus c. So hopefully you saw a variety of problems mixed throughout here, and even though you've seen a variety of them, this in no way is an exhaustive collection of methods for these types of problems. It's going to be important to do lots of examples, read through lots of examples in your book, and really try to understand what is going to be the most efficient way to get through these types of things without getting caught in some infinite spiral.